Have you ever watched a character in a video game just perfectly navigate a super complex maze and wondered, how in the world does it do that? Or maybe you've thought about self-driving cars and the thousands of decisions they have to make every single second. Well, it's not magic. It's this hidden science called path planning. And today, we're going to pull back the curtain and see exactly how these incredible algorithms find the perfect way to get from point A to point B.
But that brings up a really interesting question right away. When we say the perfect path, what does that even mean? Is it just the shortest one? Or is it the fastest, the safest, maybe the one that uses the least amount of energy? Well, as we're about to find out, the answer is way more fascinating than you might think.
Okay, so here's the bottom line. A simple path, just drawing a straight line from here to there, is pretty much useless in the real world. It just plows straight into problems. A smart path, on the other hand, is aware. It sees the obstacles and it figures out a way to get around them, creating a route that's not just possible, but actually efficient and safe. That's the real challenge we're talking about.
All right, so let's get into it. Our first step on this quest is to really nail down the fundamental challenge. What exactly are we asking these algorithms to do for us?
So at its heart, path planning is all about finding a best possible route between 2 points. But honestly, the real magic isn't just about connecting the dots. It's in the constraints. It's that whole avoiding obstacles part. That's where the actual intelligence comes into play.
You can think of it like planning a big road trip. You don't just want the absolute shortest route on the map, right? Of course, you want to minimize your travel time, but you're also thinking about saving on gas. You want to make sure the drive is safe, avoiding sketchy roads or rush hour traffic. And really, at the end of the day, you want the whole trip to be as smooth and efficient as possible. Path planning algorithms are basically trying to juggle all of those goals all at the same time.
So, finding a path is really just the beginning. The real game is making that path better. So how do we actually push these algorithms to create routes that are smarter, faster, and way more efficient?
And just how much of an improvement are we talking about here? Well, take a look at this number, 35.7%. That is not a small change.
Yep, that's how much less energy an optimized path can use in some cases. This is the real-world, tangible power of making a path just a little bit smarter. It's a massive leap forward. That is the power of optimization.
So how do they do it? It's basically a 4-step playbook for thinking smarter, not harder. First, they slash the search space. Just imagine tearing up all the impossible routes on a map right from the start. Then they use something called heuristics, which are kind of like clever rules of thumb that give them an educated guess on the best way to go. Once they have a rough idea of the path, they go back and prune it, trimming off all the unnecessary zigzags and detours. And finally, they use some really cool strategies to zero in on that perfect solution way, way faster.
But finding a path isn't always about just pushing forward. Sometimes the smartest thing an algorithm can do is figure out how to get unstuck. And this is where things get really, really clever.
Okay, so picture this. Our algorithm is navigating along and it spots what looks like a fantastic shortcut. Maybe a little cove or a U-shaped canyon. It dives right in, thinking it's found a brilliant, faster way to get to its goal on the other side.
But then, it hits a dead end. And from its point of view, deep inside that trap, every other direction looks worse than where it is right now. It is completely stuck. In the world of computer science, this is what's known as a local minimum, and it's a huge, classic problem. Now, the old-school way to solve this might just be to give up and start all over. To jump off, basically. But modern algorithms are so much more elegant. I love how one research paper put it. The goal is bypassing local minima instead of jumping off. So, how do they actually escape? Well, they have this whole toolkit of really ingenious strategies. Some might take a calculated leap of faith to a totally different part of the map. Others will switch into what's called a contour tracing mode, where they literally hug the wall of the obstacle until they find a way out. They can even dynamically change their own rules on the fly to find an exit. It's just incredibly adaptive. So, escaping traps is one thing, but the quality of the journey itself also really matters. A path can be totally correct, but still be, clumsy. So the final layer of intelligence is all about smoothing out the bumps and turning a rough draft into a truly elegant solution. I mean, just look at the difference here. A raw, unfiltered path often looks like what you see on the left. This jagged, point-to-point mess. Any robot trying to follow that path would be making all these jerky, sudden turns. It's inefficient, and honestly, it could be mechanically unstable. The goal is to transform it into that elegant, graceful curve you see on the right.
And why does this matter so much? Well, because a smooth path is a predictable path. And for a car, or a factory robot, or even a spacecraft, that means less physical wear and tear on all its parts, way better stability as it moves, and a journey that is fundamentally safer and more efficient for everyone.
Now, to get this beautiful smoothness, engineers use a whole toolkit of sophisticated mathematical techniques. You don't need to be a mathematician to get it, though. Just think of these as the kinds of tools a graphic designer uses to draw a perfect curve on a screen. They use concepts like Bezier curves to take those jagged point-to-point lines and mathematically bend them into these elegant, super efficient paths.
Okay, so we've found a path, we've learned how to get unstuck, and we've smoothed it all out. But what does all of this actually mean in practice? Let's zoom out from the code for a minute and look at the real-world impact.
And the results are frankly staggering. This isn't just theory. Real-world studies show that applying these optimization techniques can slash the total path length by over 28%, cut energy use by nearly 36%, and even boost the efficiency of mapping an environment by over 42%. These are absolutely game-changing numbers.
And you can see the impact of this literally everywhere. It's the core tech inside autonomous cars and those zippy warehouse robots. It's guiding spacecraft and flying unmanned drones. And it's right in your hands, making video game enemies seem so smart and helping your ride-sharing app find the absolute most efficient route to you.
Which brings us to one last big thought. The perfect path isn't just about math anymore. It's about our values. Is the best path the fastest one? The most scenic one? The one that uses the least fuel? Or the one that's the absolute safest for pedestrians? As these algorithms take on more and more responsibility for navigating our world, the really interesting question becomes, how will we define the best path forward?